originally prepared. And I'm actually extremely happy about it, because the reason I'm not going according to plan is that there were so many questions which slowed me down. I decided to cover less material and to answer more questions. So I would therefore encourage you to continue to ask questions, and the more you ask, the better. It also gives me some feel of where the audience is, because some people came to me afterwards with questions after the talk, and I wish they asked these questions during the talk, because I think others could have benefited from it, but it also gave me some more feeling of where, of the level of the audience, and I realized that the audience is far more diverse than I had originally thought, both in terms of seniority and in terms of research experience and background knowledge. So if you have questions, just shout, and I'm here. I have material here for 6 more lectures. On the other hand, as I said at the beginning, there is no curriculum that we have to cover, and therefore, whatever we do is fine, and if not, you can read about it later. So we finished yesterday. So yesterday we discussed particle-vortex duality. We started with the simplest one, and which is very well established. And then we derived from another duality, which I will review here. So that's a new duality that we derived. Let me remind you of the terminology. Lowercase is a dynamical field. Uppercase is a classical background field. This notation is not an equal sign. The left-hand side is not equal to the right-hand side. But the functional integral on the left, or the dynamical field, over the dynamical field, is the functional integral of the right over the dynamical fields. Also, we use Euclidean signature, and we slightly mix notation. This is not form notation, and this is with form notation. Hopefully this would not be a problem. The notation here is that we are in the infrared. So in the UV, short distances, we can add a phi square. We have an arbitrary coefficient in front of the phi to the 4th. And the gauge fields could also have kinetic terms. But we flow to the infrared. We assume there's a non-trivial fixed point. And we tune the parameters to sit on the fixed point. And that's true both on the left and on the right. And therefore, there is no free parameter here, and we did not include an explicit phi square term on the left. I'd like to make several more comments. So that's what we did yesterday. And we mapped the operators. So the first operator we identified was a fermion operator, spin half, which we said is phi dagger, the monopole operator on B, and it was related by the duality to phi hat dagger, the monopole operator of B hat dagger. And what I really want to emphasize is the Lagrangian. So even if we ignore the classical fields, the Lagrangians are not the same. There's a plus sign here and a minus sign here. Also, the field A, to linear order in A, we have a minus sign here and a plus sign here, which means that the monopole operator of B carries charge 1 on the big A, and therefore the monopole operator of B hat carries charge -1. And therefore this thing carries charge 1, but we have M here and we have M dagger here, so they both have charge 1. And similarly for the electric charge. Maybe I made a mistake and I don't need a dagger here. No, I do need a dagger. This is charge 1 and the minus 1. I do need a dagger. The rule is always to trust the notes, not what. So this is an operator of charge 1 and spin a half. So it's the A charge is 1, and the spin is a half. That's a fermion. The other operator that we matched is phi absolute value square, and that's mapped under the duality with a minus sign, phi absolute value square. In this deformation, so then we said that this theory is really time reversal invariant despite appearance. So if we look at this Lagrangian, we say, look, it's not time reversal invariant, it's the Wilson-Fisher theory, coupled to a U1 gauge field at long distances, and the U1 gauge field has Chern-Simons level 1, just ignoring the background fields. Here we have the same theory, but the level is -1. So neither of them looks time reversal invariant. In fact, one of them is the time reversal image of the other. The fact that they are dual to each other means that this theory is not time reversal invariant at short distances, but it becomes time reversal invariant at long distances, because the duality relates them. And the fact that there is a minus sign here means that under time reversal, this operator is time reversal odd. Which is very strange. It's a scalar field theory. We add phi square. Why is it time reversal odd? But the duality tells us that it is. Flat space or small metric. I allow even a small metric, and I even told you how the gravitational counterterms are mapped between the two sides. Now we can put it on an arbitrary manifold. This thing can be put on an arbitrary manifold because I was very explicit about the metric, and there's a very explicit prediction that if you put the theory on an arbitrary manifold, you compute the partition function, you'll get the same answer on both sides, provided you include all these background fields, all these terms in the background fields. So it's a well-defined statement. And the time reversal invariance, so first of all, it's surprising because this theory is not time reversal invariant at short distances and becomes time reversal invariant at long distances because of the duality. Time reversal that appears as a symmetry at long distances acts in a non-local way. It maps phi roughly to phi hat, and it maps phi square to minus, oops, I left out the hat, the phi hat square. So the theory has an emergent time reversal symmetry at long distances. It doesn't have it at short distances, but it has it at long distances. I would like to write it more explicitly, what time reversal does to the system. So let time reversal transformation, and I'm acting on the Lagrangian. So we have dB phi square minus plus phi to the fourth plus I over 4 pi bdB plus I over 2 pi bdA. That's what we have on the left-hand side. So let's reverse the orientation. So that's equal, not dual to, but actually equal to dB phi, value square, plus phi to the fourth, minus I over 4 pi bdB, minus I over 2 pi bdA. I just acted with time reversal. So I reverses the orientation of the manifold. And now I can use the duality, moving some things from the left-hand side to the right-hand side, and write that as dual to dB hat phi hat, absolute value square, plus phi hat absolute value square plus I over 4 pi b hat db hat plus I over 2 pi b hat dA plus I times this combination that we defined last time of, is essentially this thing. To the 4th, thank you. Thank you. Sorry about that. And this is this combination, which is essentially this. So looking at this, it looks like on the time reversal, these look the same, but there's a new shift. So if we don't have the background fields, this system is time reversal invariant, but in the presence of background fields, this time reversal symmetry that emerged is an anomalous symmetry. Because when we perform time reversal transformation, what we find is the original Lagrangian plus a correction term. This is the anomaly. No, well, it's passive and active of transformations. I started with the left-hand side, acted with t, so I reversed the orientation of space-time, and that just puts minus signs here and here. Then I'm using the duality. In fact, I'm using the time reversal image of the duality. So when I write it in the headed variables, I have plus here and plus here. Sorry, we have plus here and plus here, and the correction term was added. I could have started from the left-hand side. If you want, I can do that. I could have started with a minus sign here, here and here. Time reversal would maybe plus and plus. Then I could just copy what I have there. We also analyze what happens when we deform the theory by this phi square. So on one side, we got 0, and on the other side, we got this I. So all these features are the same as the free fermion theory we discussed yesterday. All these properties of this theory. So this is a theory that at long distances has time reversal invariance, a surprising time reversal invariance. It's a new time reversal invariance. It's a time reversal invariance that acts non-locally on phi. Because roughly speaking, time reversal of phi is phi hat. So time reversal takes the original variables and maps them to the dual variables. That's a symmetry that emerges at long distances. And phi square, which was time reversal invariant in the original description, becomes phi hat square with a minus sign. So the mass term is odd under this new time reversal symmetry. So this system is time reversal invariant in a surprising way. In a non-local, time reversal acts in a non-local way in the original variables. But it acts locally in the end of the day. Number one. Number two, that time reversal symmetry has an anomaly, and the anomaly is precisely the anomaly of a free fermion. Also, the system has a fermionic operator which charge 1 under the global symmetry, and it exists on both sides of the duality. And it has an operator, a relevant operator, which is odd under time reversal. This guy. So that looks like the free fermion. So at this stage, we make an assumption. That's an assumption. So far, it was almost rigorous. The only thing we did not rigorously prove was this particle-vortex duality that we started with. But there's huge amount of evidence that there's almost a proof that it's right. One needs to dot the I's and cross the T's, but this particle-vortex duality is right. We derived from it this, and now we make an assumption. This is the first time we make an assumption that this new theory that we derived, the infrared limit of this thing, is the free fermion theory. So that's a conjecture. And the conjecture is the statement that the theory that we had there on the left, over there, is dual to I psi bar d slash a psi. To be consistent with all our notations, I will write it explicitly. This is dB phi absolute value square plus phi to the fourth minus I over 4 pi dB minus I over 2 pi dA, and that's also dual to dB hat phi hat absolute value square plus phi hat absolute value to the fourth plus I over 4 pi b hat dB hat plus I over 2 pi b hat dA plus I over 4 pi AdA plus 2I is gravitational Chern-Simons term, and I flipped the sign so that this will be consistent with the conventions of the anomaly that we had yesterday. So this is, if you wish, a triality. Two bosonic systems that do not have time reversal invariant, they flow to a fixed point, which is time reversal invariant, but it's written in terms of fermions. So this is a bosonization formula. So what we have is two distinct UV theories. So phi and B, and here we have the theory of phi hat and B hat, and they both flow at long distances to a non-trivial fixed point, which is the theory of a free fermion. So this is a conjecture, but it's a very explicit conjecture. The conjecture is that this theory at short distances, we start with this theory at short distances, we end up at long distances with the free field theory, which is the free fermion theory. And similarly here, we start with this theory at short distances, we also end up at long distances with the same free field theory. And this operator that we discussed before, phi square, which we said is minus phi hat square, who can tell me what it is mapped to in the fermionic language? Psi bar psi, very good. Excellent point. So we identify, as we wrote there, the monopole operator, the with phi dagger, was mapped to the monopole operator dagger of B dagger, phi dagger, B hat dagger, and that is mapped to psi, and the dagger of that is mapped to psi dagger. But the operator psi bar psi does not have any monopole. It's kind of a monopole anti-monopole, and the lowest operator that we find there is the master in psi bar psi. So psi bar psi is a composite. It's psi here and psi bar here. We bring them together. We're doing the OPE. We have an infinite number of operators. The lowest dimension one is this psi bar psi. So the basic fermion here in the fermionic language, which is a free field, is a complicated monopole operator in the bosonic language. These are different monopole operators in the two sides here. So there's a monopole operator here, which is mapped under the duality to the monopole operator here. And the fact that they're mapped to each other, they're mapped to a particular operator at long distances, and that particular operator is a free fermion. Well, operators in Euclidean space always commute. So I'm using Euclidean signature here. Well, we have to define more carefully what happens when we bring phi near M. Now, phi is not gauge invariant and M is not gauge invariant. This combination is gauge invariant. And I mentioned yesterday that it's actually quite subtle because the operator M, since it carries magnetic charge and phi carries electric charge, phi has half integer angular momentum, so one has to be careful in working out the quantum numbers, and that's what I did yesterday. This is where the spin a half came from. Right? Somebody told you that this duality is right. And we established that it has a fermion operator. That's easy. That we see at short distances. There's an operator which is gauge invariant, and has charge 1 under the global U1 symmetry and spin 1/2. That's something we see at short distances. At short distances, it's a very complicated operator. It's a monopole operator. And correspondingly, its dimension is very high. Right? It's not something that the things that you write out of polynomials in the fundamental fields have small dimension. 5, 7. This thing is very high dimension because it's this complicated non-local thing. As the renormalization group does its job, the dimension of this guy goes down. Now, the fermion at low energies, the free fermion, has dimension 1/2, dimension 1. Dimension 1 in 3 dimensions. So the dimension of this guy, which was spin 1/2, starts going down, and there is no guarantee it will hit the value 1 at long distances. It could run, and then stop at dimension 2.3. Aldai will tell you how to compute these numbers. So there's some number there. We conjecture that the number is 1. Why do we conjecture that? Because if we conjecture that the spin is 1, that the dimension is 1, so if we conjecture that the dimension is 1, then it is going to be free, for reasons that Aldai explained to you. And not only that, if we conjecture that, then the long distance description is in terms of a free fermion. And then some of the facts we noticed before become natural. But it is an assumption. It is an assumption. All the operators I did not write down. There was pi to the 4th with an arbitrary coefficient, pi squared with an arbitrary coefficient, and the gauge coupling. No, that's a deformation. Okay, I should have said it better yesterday. At short distances, we start with this theory. What did we call it? R or mu? That's a renormalizable field theory, and it's characterized by some G, and by R, and by lambda. These are dimensionful parameters. We start running, and these parameters get bigger, interactions become stronger, and we find something. Now, we say that in the infrared, this R will be a relevant operator. So I'm allowing you to tune it. I'm tuning it to a special point where there is a transition. Just by looking at this theory, for very large positive R and very large negative R, we know that it has different phases, where it's phi either condenses or not. So at long distances, we have 2 phases, and as we tune R, there's a phase transition between them. That's we know from here. Now, we go to this fixed point, lambda and G are essentially fixed. So what we said that at long distances, we can forget about this guy, and we set lambda to be 1, just to tell us that we are really at long distances. We could have also killed this guy. It doesn't matter. All we are left with at long distances is this parameter R that we tuned. So when we discussed the operator phi square, what we meant is the deformation in R around this tuned point. So at short distances, there is some R that was tuned to some number, 3 in some units, 7.5, and your number might be different than mine, and you use a different regularization scheme, so you'll have a different number, value of the number, but that's not important. We both tune to the fixed point. That's a well-defined thing. We both to the fixed point, and then we say, let's call R equals 0 the value at the fixed point. And that way we can communicate even though we use different regularization schemes. This is kind of a renormalization group 101. I've not done it yesterday, but I'll leave it as an exercise for you, and the answer is in the literature, in the references I gave, that if we start from the bosonic theory here, and we turn on phi squared with a positive coefficient or with a negative coefficient on the 2 sides, we can work out the spectrum. For example, if we turn phi with a positive coefficient here, then phi becomes massive. We are left with just U1 level 1. We can integrate it out. and find this, say, I, long distances. But the spectrum includes the phi quanta. But the phi quanta are not gauge invariant. And to make them gauge invariant, we have to dress them with the gauge fields, etc. And we make these quanta being particles with a spin a half. And similarly here, we get particles with spin a half from phi hat. Another way of saying it, we could have acted on the ground state with this object, and we'll get a particle with charge 1 and spin a half. So we can match the spectrum of these particles between the two sides. Is this global U1 symmetry. It's unbroken on both sides. It's unbroken. There are particles that carry the charge, and they have spin. And the basic particle, which has charge 1, has spin a half. And in the fermionic language, we identify this particle as the free fermion when we deform by a mass. So I leave it as an exercise for you to work it out explicitly. So then, yes, partition function. We have to also to match all the correlation functions. The response, the partition function in the fermionic theory gives us the same two answers, depending on the sign of R. No, it's not enough. It's not enough, because the theory has many correlation functions. We have to match all the correlation functions. It's very suggestive. So what did we see? We say that this theory has, at long distances, has the same symmetries, the same, when we deform, the partition function is the same. We didn't check the correlation functions. The local operators have the same quantum numbers, but we did not check that all the correlation functions at long distances are the same. There's something to prove here. And I think actually that proving it will teach us a lot of quantum field theory, because this duality should surprise everybody. It's extremely surprising, because we have a theory of bosons on one side and a theory of a free fermion at the other side. We have a theory of bosons interacting with each other, and a free fermion comes out. So it's not a theory of interacting fermions. A theory with interacting fermions, I would say, is less surprising. Because a theory of interacting fermions, we don't really have the fermions, they interact, it's complicated. And then we really need the Alday presentation of the field. There are some operators, and they have some correlation functions, and these are some numbers that we might compute using bootstrap or numerics or whatever. Here, we give a much more physical picture of what the infrared is. The infrared is a free fermion theory. We start with bosons, and the spectrum includes a massless free fermion. Now, when we deform the theory and we discuss these particles, which are the phi quanta dressed appropriately, or the phi hat quanta dressed appropriately, or the monopoles, or the vortices, etc., all these objects can be thought of as starting their life as a scalar phi. But since the scalar phi interacts with the Chern-Simons term, it acquires spin. This thing was known since the early 80s. And it was known under the name, in the condensed matter literature, this is known as flux attachment. Flux attachment is a phenomenon that if you take a particle in 2+1 dimension, and you let it interact with a Chern-Simons gauge field, the particle acquires new spin and new statistics. That's known as flux attachment, and it is extremely important in the study of the Hall effect, especially the fractional Hall effect. That's kind of the main tool that is being used. That's, of course, very nice, but what we say here is a statement which is much, much stronger than that. We are not saying that a massive particle, scalar particle, with attached flux to it, it becomes a massive fermion. That we've already known from the 80s. What we say here is that this particular scalar theory flows to a free fermion, which means that a massless second quantized theory of interacting scalars, and I underscore all these words, massless as opposed to massive, second quantized as opposed to first quantized, and interacting as opposed to free. All these things together make us a free massless fermion. This is far stronger than the flux attachment picture. Now, if we assume that this duality is right, then we derive the flux attachment picture. So the flux attachment picture is a consistency check of this duality. But the statement here is considerably stronger. This is a statement about all correlation functions at long distances. All correlation functions at long distances of this theory, complicated operators, monopole operators, etc., are the same as in the free fermion theory. This is a much stronger statement. And the flux attachment is a consistency condition. Now, we could have run this story in reverse. I could have started yesterday and saying, you know, let's postulate that these three theories are the same. In fact, it's enough to postulate that this is the same as that. Just 1 second. Yeah? There are, I can mention some supersymmetric extensions. I can assure you that the thought crossed my mind. I could have started the logic with just postulating this duality. I pulled it out of a hat. Somebody told you that this is the correct answer and left the room. You didn't get to ask why. If you assume that this duality is right, you can run all our reasoning backwards and derive the particle-vortex duality. Basically run whatever I said in reverse. And then you would present particle-vortex duality as a consistency check of this duality. Now, this is common in dualities, that you have lots of dualities. Some will imply, assuming some of them you can derive others, but you cannot derive, say, assuming 1 and 3, you can derive number 5, but assuming 5, you cannot derive 1 or 3. So different subsets of them allow you to derive others, but not the full thing. Now you think about supersymmetry. One of the motivations for this picture is actually from the supersymmetric world, rather than the other way around. The history of this is extremely interesting. I think I alluded to it in the first talk I gave. And you have supersymmetry, you can ask, is it then, how many supercharges we have? So there is a theory with n equals 2 supersymmetry, which looks a lot like this duality. This is three-dimensional supersymmetric QED, and more to the point, a theory with half the content of fields. So it's U1, level a half with a single chiral superfield. This theory has been subjected to many tests, and that's dual to a free chiral superfield. So that duality had been subjected to many, many tests using much more powerful tools than what I described here. Again, it cannot be rigorously proven. It can almost be rigorously proven, but there's no doubt that it's right. It's connected to all sorts of dualities in string theory. People did localization computations and computed various partition functions. It's quite miraculous that it works. Nobody has any doubt that it's right. If you assume that duality is right, you cannot quite prove this one, but you can almost prove this one. But the structure of it, of some theory interacting with scalars, with U1 level 1, is the same as a free fermion, is very similar to what we've seen there. So somebody who played for years with these supersymmetric dualities, like some people in the audience, should not be shocked by this statement. They should only be shocked and say, oh, it's even true without supersymmetry. But other than that, oh, we've seen similar things. We have seen a theory of interacting chiral superfields with a U1 gauge field, becoming at long distances a free theory. We've seen examples of that. And not only we have seen them, these examples were subjected to many more tests than we can do here. So again, this is not a proof, but it suggests that this is true. And this was really one of the motivations for this picture. Okay, I've just finished yesterday's talk, according to my schedule. And I first thought that my last talk will be in a totally different spirit and will be given with slides. It's more like a seminar. But given that I have 43 minutes plus time for questions, I decided to change it. And what I'll do now is give you some outline of how all these pictures and all these dualities can be used to shed light on the dynamics of three-dimensional field theories. So the dynamics of three-dimensional field theory has been interesting for many years, for many different reasons. It's connected to things in string theory. It might be a toy model for QCD in 4 dimensions. It might be related to things in condensed matter physics. And these three-dimensional field theories also occur in various string constructions. We know a lot about the supersymmetric versions of these theories, but the picture without supersymmetry has been confusing and controversial. There's a lot of numerical work. There's been a lot of progress. And people have used a lot of tools like numerical simulations or various large N techniques. The theories are labeled by terms of fermions, so we can label them, can dial the number of fermions. We can change the gauge group. The gauge group could be U1 or UN or SUN or SON. We can change the representation of the fermions. We can put Chern-Simons terms. And the question is, what do all these theories do? For simplicity, let's just focus on theories of fermions coupled to some gauge field, maybe with some Chern-Simons term. What do they do as a function of the gauge group? If it's SUN, it's a function of N. Other groups, if it's U1 or UN, what it does. Depending on how many fermion flavors we have, if it's in the fundamental, we can also put the fermions in the adjoint. We can also turn on Chern-Simons term and ask what does it do as a function of K for the dynamical fields. And there are many questions, and we'll be able to prove very little. But there are various tools that we could use to guide us to the right answer. For example, something we've already done here, we can give the fermions large mass, positive or negative, integrate them out, and as we integrate them out, we are left with a pure gauge theory with the Chern-Simons term. That theory has a gap, and at low energies, it is just a topological field theory that we know. So this is one tool. The other tool is that we can take the level K to be very large. The level K is very large, the fermions are very heavy, the gauge fields are very heavy, they can be integrated out. And then to first approximation, what we have are just free fermions, because the fermions interact only through the gauge field, but the gauge fields are very heavy. And what the interaction with the gauge field does, the gauge field with their Chern-Simons term, is like kind of a Gauss law that acts on the Hilbert space and picks out the correct gauge invariant operators. So that's also a calculation we could do. So at large K, we expect a non-trivial fixed point at long distances, theory of the kind that Aldai has been discussing, where we have some topological field theory for positive mass, some topological field theory for negative mass, and then a theory of essentially free fermions at zero mass. That's what we expect at large K. And at large M, the picture is also similar. So the picture we would expect in general, that we have some gauge group G, with some level K and some fermions. And this is the mass of the fermion. And when the mass is positive, we have some TQFT, some Chern-Simons term. And when the mass is negative, we have some TQFT prime, which can be written as some Chern-Simons term for the gauge group G with the level K. Perhaps the level is shifted a little bit because of the fermions we integrate out. And in here, we have a non-trivial fixed point, which is the transition point between positive and negative mass. And this theory is essentially a theory of free fermions, small correction to the dimensions, with some rule how to pick from them the gauge invariant operators that depend on the gauge group and the level. So that's what we expect in this region. And then we ask ourselves, what happens when K is not small? If K is not large, K is small. What happens when the mass is not? When the mass is not large, when the mass is small. So if K is small, this fixed point, if it exists, is there such a fixed point or not? What would we expect at long distances? So we can put together all the facts that we know from various limits, and all the facts that we know from numerical work, and all the facts that we know from the duality we've been discussing. We can also extend these dualities in many ways, some of them I'll soon mention, and see whether we can come up with a coherent picture which is consistent with all the facts that we know. So it's again a conjecture, because we can't prove it. We can prove it only in certain limits. Some of the dualities can be checked. Some of the dualities are on firmer footing than others. But let's see whether we can come up with a scenario which is consistent with all the facts that we know. And it's often the case in these theories that you cannot come up with any conceivable scenario because the constraints are so powerful. So if you can find a constraint, a scenario that satisfies all the constraints, you have some level of confidence that it's right. Now, I've been doing playing these kind of games for decades, especially in the supersymmetric world. And I must confess that in the supersymmetric world, we work on much firmer ground. Because in the supersymmetric world, we can perform many more tests. And many assumptions that we have to make here, we don't have to make there. But the intuition is still there. So I'm going on a limb and saying that I believe that what I'm going to present is what these theories really do, but I cannot prove it, and I'm walking on very thin ice, very thin ice. I hope I convince you that the picture is sensible. So let me start with the first example, which is QED. We are going to start with U1 level K with NF fermions size. And as we discussed yesterday, K should be NF over 2 mod 1. So if NF is even, so again, K, we define it to be the average between what happens with positive mass and with negative mass. So that's the definition of K. And it has to be half integer when NF is odd, and it's an integer when NF is even, because then this anomaly is absent. So what do we know about this theory? That's what we have at short distances. And we just follow our recipe in general as a function of the mass. And for simplicity, let's all the fermions have the same mass. So when the mass is positive, then K is shifted up. So here we have a topological field theory, K plus NF over 2. And at negative M, we have U1 level K minus NF over 2. And to make the discussion simple, or let's first limit ourselves to K bigger than NF over 2. So K is bigger than F. So when K is infinite, we know what happens. This is what I said before. For positive mass, we have this. For negative mass, we have this. This is essentially the computations these are essentially the computations we did yesterday. And we have two topological field theories. And at very large K, there's a non-trivial fixed point here. And we are going to conjecture that the same qualitative picture persists for all K larger than NF over 2. That's an assumption. That the picture at large K persists for low values. Because at large K, the gauge field is very heavy. So it's very heavy, it doesn't participate. So what's the dynamics? The dynamics are light fermions. We have NF light fermions. That's a free field theory. What do the gauge fields do? They tell us which fermions to keep, which combinations to keep, which combinations are gauge invariant and which are not. And in power series in 1 over K, they will correct the anomalous dimension. But they're not going to ruin the fact that these are essentially free fermions. And people have been computing these power series in 1 over K. Especially the Indian group has been doing a lot of work here. Maybe you're one of them. No. So other Indian, I think Shiraz has led a massive enterprise computing these theories at large K. Now, so this is a conjecture. And now I'm going to add to it another conjecture. This is a fermionic theory. There is a dual bosonic theory that flows to the same point. Level -1 with NF scalars pi, the fundamental of this group. So this is very similar to what we discussed earlier. This is a boson-fermion duality. This is a fermionic theory. This is a bosonic theory. That's an assumption that these two theories are dual to each other. We cannot prove it, but we can check it. So for one thing we could do is let's imagine that phi has positive mass square. So when phi has positive mass square, the first approximation, when it's very heavy, we forget about it. So what do we have at low energies? At low energies, we have SU k plus NF over 2, level -1. It's a topological field theory. And sure enough, these topological field theories are dual to each other. And this duality can be rigorously established. This is known as level rank duality. So there's a mathematically rigorous derivation that this topological field theory is the same as that. So the low energy dynamics in this phase of this theory is the same as that. Let the fermions now have negative mass square. What do? They Higgs the gauge group. As they Higgs the gauge group, we have NF phi's. So the first reduces the rank by 1, the second reduces again by 1, etc. And we end up with SU k minus NF over 2, and the level doesn't change. So that's the Chern-Simons term. And sure enough, these two topological field theories are dual to each other, again by level rank duality. So what can we establish? We establish that this bosonic theory and this fermionic theory both have the same two phases. And not only do both have two phases, the phases are the same. This is not to say that the fixed point that interpolates between the two phases are the same. But we conjecture that this theory, this bosonic theory, flows to the same fixed point as this fermionic theory. Sorry? So the scalar field, that's an excellent question. The scalar fields have a phi to the fourth interaction and a phi square interaction, and they couple to the gauge field. The kinetic term couples to the gauge fields, very much like what we said earlier today. And again, we flow to the infrared. We tune the mass square to hit the fixed point. The phi to the fourth does what it does. The gauge coupling does what it does. Okay. This one, that's the flow from the UV. So this is the point M. This is the point we will call M equals 0. No, you don't flow from here or here. You flow from here. So you change the mass here, and you either land here or you land here. You change the mass here, you either land here or you land here. Now, this theory is a U1 gauge theory, and as such, it has monopole operators. So the fermionic theory has monopole operators. Whose quantum numbers depend on K and NF. Depending on what K and NF are, there are some quantum numbers. And not only that, they are in some representation of a flavor SU and F that rotates the fermion. It can be shown that they are dual to baryons made of phi. So essentially phi to the power K plus NF over 2. It's an appropriate contraction of the indices. So this is another test of this duality. This theory has some interesting monopole operators. There's a global U1 symmetry. So what are the symmetries of this theory? There's an SU and F that rotates the fermion, and there's a U1, which is the monopole number. What are the symmetries here? There's an SU and F that rotates the fermion, but there's also baryon numbers because we can rotate the fermions by U and F. So this global symmetry matches this global symmetry. And the charged object under it here is a monopole operator. The charged object here are various mesons and baryons, and they map correctly. So bilinears of fermions are mapped to bilinears of fermions. These are the mesons. And the baryons from here are mapped to monopole operators here. There are more tests of this duality that we can perform. Yes, it's very surprising. You could also say that it's surprising the other way around. We have a non-abelian theory, which is dual to an abelian theory. One of them has fermions, the other has bosons. So if somebody told me a few years ago, look, this theory is the same as that, I would say, this is ridiculous. There's no way this would be right, because it's so surprising. The tests are incredibly impressive. And there are more tests I have not even given you all the tests. In 4D, it's completely different. This is very, very three-dimensional. It's very three-dimensional. Let's compare this picture with when we try to make K smaller. So we just go to U1 level K and let K be an F over 2. With NF fermions. Notice that what we did before, earlier, we did NF equals 1 and K equals a half. That's what, oh, I haven't done that. I could have done it. But this is a special case of what we're doing here. Everything is still good. We have here SU and F. I just copy what we had before, level -1 with 5. And here we have U1 level in F, which is level rank dual to SU and F level -1. And on this side, what do we have? We have NF scalars that start Higgsing, and we are left in the end of the day with one free scalar. On this side, we end up with U1 level 0, and we've already said that these two theories are dual to each other. So in this case, when K is bigger than NF over 2, we have two gapped phases with topological field theory. In this special case, we have a gapped phase here with the topological field theory and a massless scalar field on the other side. And that's reproduced by the two pictures. Now, in the very special case, NF equals 1 and K equals 2, what we have here is a standard QED, U1 level a half, with one side. This is QED. And we now claim that it is dual, so SU1 is a trivial theory, it's just a Wilson-Fisher theory. It's a special case of this. In fact, this particular special case can be derived using the techniques of earlier this lecture. Earlier this lecture, we had some bosonic theory, which turned out to be dual to a free fermion. And the way we derived that, we had some classical fields. In another theory, we make them boson, made them dynamical, add the Chern-Simons term, integrated out what we could, and we derived that duality. So all the dualities we discussed in the first part of this lecture imply this duality. So this special case is on firmer footing than this more general case. So it's again a picture of all these dualities. When we have one duality, we can derive others. That's an assumption. And then that these other dualities could be special cases of more general dualities. Yeah. It's not free. It's not free. It couples to a gauge field.
It is similar to what we did with the earlier part where...
No. First of all, so we discussed three cases. This came very large. Then we discussed a very special case of K, where we have a free scalar here. And now we're going to the very, very special case, where we substitute NF equals 1. So here we have, again, this is trivial. And this is free scalar. This is what we would expect from this theory. On the fermionic side, we would say, oh, here we get U1 level 1, which is trivial, and here we get U1 level 0, which is just a free photon, which is dual to a free scalar. So that's what we get. This picture, this gives us the same two phases. This is another theory we discussed that has these two phases. And the duality between this and that, I did not do it here, follows from other dualities. So what did we do today? What did we do yesterday? We started from particle-vortex duality. Then we gauged the symmetry with the Chern-Simons term, and we derived a new boson-boson duality, which related two different bosonic theories. Then we analyzed them, and we realized these theories look a lot like the free fermion. We assumed it's equal to the free fermion, dual to the free fermion. Something I did not do for lack of time. You can do that as an exercise, and it's worked out in the references I gave. Take this boson-fermion duality that I discussed, promote the classical gauge field to a dynamical gauge field, and derive, on one side, you derive this theory. And just follow your nose and do the same manipulation on the other side, you will derive that one. So when we discuss particle-vortex duality in the bosonic theory, this is what we did yesterday. We discussed particle-vortex duality. We discussed this particular theory. Now we say, and we said that it flows to a certain fixed point, a fixed point that was analyzed with enormous detail over the last several decades. Now we say that QED in 3 dimension follows to a non-trivial fixed point, and not only that, it's the same fixed point of the Wilson-Fisher theory. And that follows logically from the assumption I made earlier today of one Fermi, that this bosonic theory is dual to a free fermion. It just follows from it. The same line of reasoning gives this statement. So this is something that can be checked numerically. If it works numerically, Ray, that gives us more confidence in our dualities. If not, this entire structure goes away. Just 1 second. And now we see how this particular statement, of U1 with one fermion, level a half, which is on firmer footing than the rest, fits nicely with this generalization. This generalization fits nicely with this generalization. Yes, the question. This one? Yes? This duality is a mathematical fact. That's not an assumption. I cannot use this to derive this. This duality contains much more information. It's at one corner. It coincides with the known duality. So this duality is a consistency check of that. The fact that we landed on a correct duality gives us confidence that what we're doing is right. But it's not a proof. We cannot go backwards. To the question. Yeah? Absolutely. Absolutely. That's what I'm going to do soon. Oh, we have 18 minutes. I can do that. So, since I was asked to do that, let me tell you what happens if I have SUN. So that was QED. The next thing to do is QCD. So QCD is an SUN gauge theory. And that all this was worked out in, what I've said so far as references was worked out in a lot of detail by various papers, especially this particular thing with n equals 1 in a paper I wrote with my student, Hoshen Shin. But pieces of it appeared earlier. In fact, a lot of it had appeared earlier, so we shouldn't get credit. But that paper is the latest, and it has a lot of references to earlier papers. Especially this duality with this particular duality, which I'm soon going to generalize, is a very special case of a duality that Aharoni wrote down based on other dualities which were derived at large n. So this duality is the n equals 1 version of the duality that was derived at large n by the Indian group led by Shiraz, Minwala, and Spentawadia. So what I'm trying to convey is that when I state such a duality, it looks like, where did this come from? There's a huge body of work that had been done before. Some of it is rigorous, some of that is almost rigorous, and some of that is conjectured, but with a lot of evidence. And this is kind of trying to interpolate to find a coherent picture that includes all these facts. So it's not that somebody just woke up one morning and said, well, let's examine this duality. There's a lot of background that leads to it. So let's discuss the SUN theory. So this is like QCD. It can have a level K, and it has NF fermions in the fundamental representation. We can call them quarks. And very much like what we did before, we're going to assume that K is large, and specifically, would like K to be larger or equal, I'll write it here, K larger or equal to 2. So again, we have two phases. So you see, after a while, you get used to it because the story repeats itself. So we have SUN. When the mass is positive, the level is shifted by NF over 2. And when the mass is negative, the level is shifted by N over 2. And there is a dual description, a bosonic dual description, which is U K plus NF over 2, level minus N, with NF scalars. And again, with the 5/4 interaction, and with the phi square, and the gauge coupling, and we flow to the infrared, and we tune the mass square such that we find a non-trivial fixed point. And the claim, in this form, it was first written by Aharoni, and that's the large N limit of that is what was worked out originally by the Indian group, that these theories are dual to each other. And indeed, as we had before, this is level rank dual to UK plus NF over 2 level minus N. So if all the fermions have positive mass, you just forget about them, and we have this topological field theory. And here, the gauge group is Higgs, so we get K minus NF over 2 level minus N. And again, we have level rank duality here. And in between, we have a non-trivial fixed point. That's the assumption. And both in the abelian case and in the non-abelian case, if you accept the duality with one value of the number of flavors, you can decouple one flavor at a time and derive the duality for one flavor less. So the assumptions are not independent. Also, you can move between dualities using the tricks I used earlier in this lecture and a little bit yesterday. There's a global symmetry, we can promote it to a gauge field, integrate stuff out, and derive a new duality. So lots of relations between them. But the bottom line is that this QCD-like theory flows at long distances to a non-trivial fixed point, and the same non-trivial fixed point has a bosonic dual. Now, again, this is an assumption, but it's a very explicit assumption. Very explicit, it's either right or wrong, and that's what it does. This is the statement, and if it's wrong, then you made a mistake. But the evidence for that is quite large. So again, the Indian group analyzed it when K and N are both large, the limit that both N and K go to infinity with fixed ratio. In that case, you can compute a lot of things on the two sides of the duality in deriving. There is also a string dual description that gives this picture. The phases match, the global symmetries match, and something more sophisticated, which is the anomalies in the global symmetries, also match. And you can use the flux attachment. So you asked me about flux attachment in the non-abelian case. That's what it is. So we have the flux attachment picture. That's exactly the next thing I'm going to comment. The literature is my paper. I am fully aware of it. So let's look at this thing. What did we do here? The fermionic theory makes sense, so we flow to where we flow. In the bosonic theory, I said that we have these two phases. In this phase, we gave the fermions, the bosons, positive mass square. And as we give them positive mass square, we can ignore them and they give us this. When they give the bosons negative mass square, the scalars start condensing, and every one of them reduces the rank of the group by 1. But if NF is too large, and we should end up with this, but you see that if we violate this inequality, the argument here, let me write it more clearly, becomes negative. So that doesn't make sense. That tells us that this story cannot be true when the number of flavors exceeds this bound, because then we are going to get something negative here. That's the origin of the statement said before. More physically, imagine we have many more scalars. And with positive mass square, we're going to get at low energies this gauge group. With negative mass square, some of them Higgs the gauge group, but by the time the gauge group is completely Higgs, the remaining scalars become massless. Very much like what we saw here, that is, we had too many scalars, we have U1 level 0, which was okay. Here it was reproduced in the fermionic language. But with fewer fermions, with more scalars here, that's not what the fermionic theory gives us. Fermionic theory gives us these two gap phases. So we have a duality, which is kind of the analytic continuation of this one to more flavors, but it cannot be right. This is an example of how duality could fail. You know, we check one of these things, and it doesn't give us the same answer. This theory has a phase with massless scalars. This theory does not have a phase with massless scalars. So this duality is not right. Except that you can present a variant of this picture that shows that this duality is not completely wrong. That's a nice thing about duality. Whenever you have something that, you know, they have the same symmetries, the same operators, a lot of tests work, but some tests do not quite work, it might still be good for something. Perhaps not the original thing you wanted, but for something else. So let's explore what we could say for SUN level K with NF fermions when K is less than NF over 2. So this was done with Zohar Komagotsky, and the paper is in the archive. Now, I tried to convey before the intuition that large K is weak coupling, because when K is large, the gauge fields are very heavy, and they very weakly interact with the fermions. So as we crank K lower, we make K smaller and smaller, the theory becomes more and more strongly coupled. And as it becomes more and more strongly coupled, it could do more interesting things, which are not visible semi-classically. So this whole picture with the phases that I talked about today here, we had two phases, and they were both visible semi-classically. And then we conjectured various things about the phase transitions between them. We had two weakly coupled phases and a phase transition between them. But as we make K smaller, the theory has room to become even more strongly coupled. And as it becomes more strongly coupled, it could do more interesting things. So we conjecture, with very little evidence, that when NF, so let me write it like that, K is bigger than NF, and smaller than some N star, which depends on N and K that we don't know how to compute. So the range of NF, where, what do we know? When the mass is very big and positive, we should have SUN level K plus NF over 2. When the mass is large and negative, we should have SUN level K minus NF over 2. That we know semi-classically. This is just integrating out the fermions when the mass is very large. And this thing we've already discussed is level rank dual to SU NF over 2 plus K level minus N. And this thing is level rank dual to, this is U, level rank dual to U K minus NF over 2 . So another way of saying it is that when the number of flavors is too large, this thing, and I've said it earlier, will have a negative argument. That's bad. So instead of negative argument, we can do parity transformation or time reversal, make it positive and flip the sign here, and then these two are level rank dual to each other. So these are facts. There's nothing we can do about that. This phase must exist. This phase must exist. This phase is level rank dual to this. This phase is level rank dual to that. And now we propose that there are two phase transitions at long distances, not just one. And this is the correct statement in this phase. This is the correct statement in that phase. Leave more room here. And this bosonic dual that we had before really flows here. So this is U and F over 2 plus K, level minus N with an F phi. And here there's another bosonic dual, which is U and F over 2 minus K, level N with an F phi. So what do we know so far? First of all, I'm addressing that question that I was asked before. We had a duality between this and that. That was motivated by large N and all the things we said before. There is another duality between this and that. That's again motivated by large N and all the things we said before. This duality works in this phase because the fermionic theory has this particular phase with a gap phase with topological field theory. And the bosonic theory at that phase when the scalars are massive. On this side, the fermionic theory has this phase, I integrated out the fermion, and this bosonic theory has this phase when these phis are massive. But this picture could not be complete because we said that the number of flavors is too big. So if we Higgs this gauge group enough, we'll end up with massless scalars. And this could not be correct, complete, because if the number of flavors is big enough, we Higgs the gauge group as much as we can, and we are left with massless scalars. So all we need to say is that these two theories with massless scalars describe an intermediate phase. And these massless scalars, we can work out what this space is, and that's a nonlinear sigma model with an U and F spontaneously broken to U and F over 2 plus K times U and F over 2 minus K. So we propose that for this theory to be right, the fermionic theory, it's small k, when it's strongly coupled, has a phase, an intermediate phase, with a nonlinear sigma model. Very similar to the kind of physics that we see in 4 dimensions. This space is known as a Grassmannian, and furthermore we claim that this term has a Wess-Zumino term. very much like the Wess-Zumino term in four-dimensional chiral Lagrangian with coefficient n. So all the information in n is captured at low energies by this Wess-Zumino term. So again, we cannot prove it, but we make a conjecture, and the conjecture is very, very explicit. So either right or wrong. So to summarize, for positive mass, we have this phase, which we establish rigorously, and that's a phase also of this dual theory. For negative and large mass, we have this phase, which is established rigorously, and it is a phase of this one. And these two bosonic theories also have another phase, which is not easily visible from here, which give us this nonlinear sigma model. So somebody could complain, what kind of a duality is it that this theory and that theory do not have the same phases? This theory has three phases, 1, 2, 3. And this theory has only two phases, 1 and 2. And similarly here, this one has only two phases, 1 and 2. Well, the statement, this is an infrared duality, and the infrared duality is a statement only about the extreme infrared. And extreme infrared means that we are around this point. So this is where the duality should be valid. And similarly, this duality should be valid around this point. So if you know a little bit about n equals 2 supersymmetry in 4 dimensions, a very similar picture exists there. There's an SU2 gauge theory at short distances that gives us a U with two singular points. And around each of these two singular points, we have an effective dual description in terms of a U1 gauge theory. And that one gauge theory gives us a good description in the neighborhood of this one, and another U1 gauge theory gives us a good description around the other monopole point, but not both. So the claim here is that it's very similar. The parameter space is large. This UV fermionic theory captures the entire parameter space, and the two bosonic duals capture the physics around this point and around that point. Now, a lot can be said about this intermediate phase. The fact that this is the sigma model can be derived from this bosonic language. This is a weakly coupled description that gives us this phase. And the Wess-Zumino term arises from the Chern-Simons term in this theory. It is a highly non-trivial fact that exactly the same nonlinear sigma model with exactly the same Wess-Zumino term arises when we go from the other side. That didn't have to work. If that had not worked, the duality would have been wrong already.
These are valid all over the flow.
That's the
added all operators.
That's right.
But this is not.
Well, it is valid. It's not valid with the parameter. The coefficients are very large, but the small coefficient, it describes this neighborhood in the mass.
It's okay, but if you go far away, then.
Far away, then you're far from the fixed point, and then the dynamics changes. So you have to go to low energies. You have to go to very low energies with small enough mass, then the duality. So the map between the mass parameter here and the mass parameter here is a nonlinear map. Infinitesimally, they are the same, but the mass here is related in a company. So as the mass here becomes bigger, goes to even to infinity, this will only cover a small range of the masses here. I didn't promise anything about the map of operators. So that might look like, again, it's a conjecture, and you could be surprised by it, and you could be surprised that we can even say anything like that about a very strongly coupled theory like QCD, SUN with, say, we can even substitute K equals 0 for that matter. So it's an SUN gauge theory with some quarks. And we claim that at long distances, it gives us this nonlinear sigma model. Now, there's a lot of evidence that this is right. First of all, this particular sigma model for K equals 0, without the Wess-Zumino term, was proposed by Waffa and Witten in the early 80s based on absolutely different considerations. Absolutely different considerations. Second, this theory has baryons. So if you know a little bit about four-dimensional QCD, the baryons at short distances. There's also in four-dimensional QCD, there's also a nonlinear sigma model at long distances. And the baryons of QCD, how are they realized in the long distance theory? Does anybody know? Somebody said something. They should be bounded, but these are the only mesons. How do we make baryons out of them? Does anybody know? Among the more senior people in the audience? They're solitons, and these solitons are called skyrmions. And sure enough, this sigma model has skyrmions, which have exactly the quantum numbers of the baryons at short distances. And the way to see that is that the baryons here are monopole operators here, and there are skyrmions here, which are monopoles here. So you can check the quantum numbers of all these, and they work beautifully. This is another reason to believe that this picture is right. So very similar things were known in 4 dimensions, in 4-dimensional QCD, and now we have the counterpart of them in 3 dimensions. And notice the difference between QED and QCD, that we have this new strongly coupled phase in QCD, which is not there in the abelian theory. There is actually a modification of the abelian theory that gives us such a sigma model, but I'm not going to cover it here. So in view of the time, I think I'll stop here. I will just say that what I've done here was only scratch the surface of what has been done. So the first lecture was kind of a colloquium. I tried to give an overview. And in the second and half of the third, I gave some tools, not all of them. In the second part of the second lecture, and the beginning of this talk, I used these tools and I gave the references to derive some dualities. And in the last part of the talk, I tried to give you a flavor of what can be done with it to derive new results about the long distance behavior of such gauge theories. And a lot more was done. For example, we can ask what happens when the gauge group is not SUN but SON. It turns out that all sort of new phenomena happen. SPN was also analyzed. You can ask what happens if the gauge group has the fermions are not in the fundamental but in the adjoint of the gauge group. And that connects to the theory which is supersymmetric. Again, a lot was done, but not everything. But I feel that there's a lot more that can be done because this is kind of virgin territory, and whatever is done is new. And there's kind of a lot of background that needs to be learned. You have to get used to the techniques, but once you do that, the results are just pouring in. And I've had a lot of fun doing it in the last 2 years, and I also had a lot of fun giving this talk, so thank you.
Questions? QED dual might have some gravity dual. Some of the QED dual.
What will it be?
May have some gravity dual.
Okay, so I believe all these theories at finite n have a strongly coupled gravity dual. So that's not that useful. These theories at large n and at large k with fixed nf, so we're really in this regime, not in that regime. These theories with large n and large k with fixed ratio do have a gravity dual. In fact, this is one of the ways this story began. These theories have a gravity dual. These theories have a gravity dual, and they have the same gravity dual. So for fixed n and k, both going to infinity, you can vary n over k, and in one end, this theory is weakly coupled, and in the other end, this theory is weakly coupled, and these two theories turn out to have the same gravity dual. And not only that, this is a gravity dual that people had been interested in before. It's known as Vasiliev theory, which is really a fantastic example of how things work. The Vasiliev theory, which was an interesting but somewhat esoteric line of investigation around string theorists, It's a certain gravity theory which has higher spin symmetries, etc., etc. Turns out to have the same Vasiliev theory has two different field theory duals, and therefore there must be a field theory duality at large n. Then that duality was conjectured to be valid at finite n. Then we worked out its consequences when n is 1, very, very far from the Vasiliev theory, and that turned out to be connected to some ideas in condensed matter physics. And if that's not the unity of physics, I don't know what is.
Two fixed points in IR, right? So, why do you say that in the IR is also due to the coset model?
No, it's not. Okay, thank you. First of all, I cannot prove that this is a second order point. It might be first order. So that's kind of a small correction. But if there is such a transition, so if there are two transitions here, and these two transitions are separately dual to this and that, then in this language, I can derive such a sigma model. So that's not a duality. So if you buy all these things, then there is a statement that this non-abelian gauge theory at long distances gives us such a nonlinear sigma model. So this is something that is measurable. So take this system, all the fermions have equal mass, there's an SU and F global symmetry, run your computer simulation or whatever you do, and you will find that at long distances, this theory flows to a nonlinear sigma model. In other words, this SU and F global symmetry or U and F global symmetry is spontaneously broken with this pattern. This is a very explicit statement that can be verified numerically. It's not beyond reach to analyze this system numerically. People do very similar things. But that's not a duality. This is a statement that ordinary QCD gives us pions at long distances. This theory in 3 dimensions gives us pion on this manifold. This is a very concrete statement. That's not a duality. Tells us that when we make the mass bigger, or positive or bigger or negative, there is a phase transition, and that nonlinear sigma model will no longer be the good description. On the other side, we have a topological field theory. That's another statement. This part we can actually prove, this and that. And the statement of the duality is that this transition is captured by this bosonic theory. That's a statement of the duality.
Versions admit some string or M theory realization as some sort of, yeah, well, in terms of some non-compact geometry where I can decouple gravity and interpret, say, for example, the level rank duality in terms of geometric quantities?
Yes. So I'm glad you brought it up. I described this thing as coming from the large N story, but there's an equally good starting point, starting from dualities in 4 dimensions with n equals 1 supersymmetry, and their descendants that are dualities in 3 dimensions with n equals 2 supersymmetry. And some people in the audience worked out the consequences of these n equals 2 theories in 3 dimensions. So there's huge literature on the subject, which was motivated partly by compactification from 4 dimensions, partly by various brain constructions, and partly by various string singularities. So there's a whole zoo of 3-dimensional n equals 2 dualities, which look very similar to these. The various shifts by 1, and there's fermions here and bosons there, and there you have superfields on both sides. But they're very similar dualities, which again, since it's supersymmetric, people computed a lot of things, computed the S3 partition function, the S2 times S1 partition function, the elliptic genus. They did a lot of work, and they have brain constructions, and there's huge literature on this stuff. And the qualitative picture is very similar. In the formulas, if you look at the formulas from afar and, oh yeah, there's an N and an F, and the argument here is K plus an F, and the levels shift. Kind of, superficially, it looked very similar. The details are a little bit different. Well, the matter content is also different. And in the supersymmetric case, we have gauge zeros here and here, and in the non-supersymmetric case, we don't. But if you have enough experience with the supersymmetric ones, this should not be that surprising. It's surprising that it exists. You can say anything without supersymmetry. But the formulas are very similar to expressions in the supersymmetric case. And there, it is connected to a lot of string constructions. Now, there's really interesting interplay here between things which were motivated by string theory, things which were motivated by supersymmetric dualities, and things which were motivated by ideas in condensed matter physics. And they all converge on this stuff. So I keep emphasizing that these are conjectures, but the fact that the same conjectures are motivated almost independently by ideas from different branches of physics using totally different tools, using totally different line of reasoning, strongly suggested that there's an interesting story here.
And regarding this problem, what's your perspective about the major thing to do to prove this duality exactly, or it's?
Okay, I spent a lot of time trying to prove it, and I don't have an argument. In various cases, flux attachment almost gives you an argument. So for the massive particles, you can see there's a derivation of this flux attachment that derives it, but not at long distances at a fixed point. Okay, so I don't know how to prove it. I strongly believe that an explicit proof of any of these dualities would be very, very interesting and very important. This is not something I would suggest as a problem for a graduate student, because it's very hard. Many people tried it. And we could even start with the supersymmetric dualities if we are more confident that they are right. In general, there's a phenomenon in quantum field theory that now we see is quite ubiquitous. Before, I remember I would give talks and I would say it's supersymmetric, duality, this or that, and people in the audience would say, yeah, but it's supersymmetric, it's not generic. So now it's generic. This, you cannot hide. This theories that you would be interested in anyway exhibit this phenomenon, and we have no idea why it's true. This is a huge gap in our understanding of quantum field. Now, we would like to prove it, A, to see whether it's right or wrong. Maybe it's true for some range of parameters, but not others. So that would be one reason to do it. But I think it will teach us a lot about quantum field theory. There's a huge gap in our understanding of quantum field theory that these things are surprising, and we should not be surprised by such a ubiquitous phenomenon. This is a ubiquitous phenomenon. It appears all over the place. That's what we see now. And we're surprised by it. That tells us that we're not understanding it. So personally, and I've said that in my first talk, in fact, I said it also last week. Nobody from the people of last week is here. I gave a talk last week about quantum field theory, and I said that I think that understanding why duality is true is a very, very important question. And, well, I'll leave it at that. Hopefully one of you guys can. I believe it's not going to be a straightforward extension of the known techniques, because all that has been tried. So we need a new idea coming from somewhere. I really hope this will happen. Thank you.